And so good morning to our July 14th ME316 live lecture. And I'll go ahead and share my screen. I have to scroll back up to the beginning there. But I believe it was spring of 19. Us mechanics faculty got together and was just looking at the content within all of our mechanics courses, and we decided that it would be good to get at least a brief exposure to buckling and energy methods in ME316. That way you are kind of aware of that as a failure mechanism and as an additional analytical method. And that was decided upon because ME316 is a required course, so all of our mechanical engineering students have to take it. And so buckling is a topic that you'll discuss more in machine design 1, ME322. That is also a required course, so it'll go into more depth. But it's nice oftentimes to see content a couple of different times from a couple different faculty members, so it helps to stick a little bit better. And then the energy methods that we'll discuss on Friday, I typically will cover that in Machine Design 2, ME422. That's an elective, so not all of our mechanical engineering students get to see that content. And so, yeah, we decided it would be good to have just at least a brief exposure to this content here in ME316. And so everything that we've done so far has really talked about kind of stress type failure mechanisms, failure under static loading conditions, looking at axial loading, torsional loading, bending, transverse shear, and even pressure vessels, looking at the state of stress that develops in that. And so there are additional types of failure mechanisms that you can experience. One of those is column buckling. And a column is just really any long, slender beam that is subjected to a compressive axial load. So in addition to that potential for failure by yielding, just because the state of stress becomes so great that it exceeds the yield strength, you have that failure mechanism. You could have excessive deformation, but then you can also have a failure by buckling. And that's really just a sudden lateral deformation that prevents really that column from being able to further support the load. The easiest way to recognize that is just think of a yardstick. If you pull on that tension, you can pull into your blue in the face and nothing's going to happen. But as soon as you place it against the floor and place a compressive load on there, you'll see that it buckles out to the side, and then it wouldn't take much force at all to cause that to break, just because you are developing a large bending moment as it's deflecting in the lateral direction. And so we really need, when we're evaluating mechanical designs, not only looking at the state of stress, but when we have axial compression members, also evaluating, is buckling a concern for this compression member? If so, do we need to make it bigger, greater cross-sectional area so that it can withstand those compressive loads without buckling? And you'll see that on aircraft too. If you look at the older aircraft, you'll see essentially cables being used to support tensile loads. That'll be experienced in, say, an aircraft wing, and then they'll use compression struts, solid metal sections, circular sections usually, that'll be able to withstand compression loading in those areas. And so in that sense, a cable or rope is not able to withstand any type of compressive loading at all. It'll just simply bend and deflect. So they can only use the cables like that for tensile loading applications, and then compressive type struts for locations where there'll be compression in those members. The main difficulty with that buckling failure mechanism is it can really just lead to a sudden and catastrophic failure without really any warning at all. Just because at one point it's able to withstand the compressive load, and in the next instance it's not able to do that anymore. And so what it's holding up is no longer being supported, and so gravity is going to take over at that point, or whatever loading is being placed on there. And so that's really a critical nature of designing columns and compressive members, is just that sudden catastrophic failure. There are quite a few examples of that. I know the 9/11 towers in New York, that's what they indicated was the ultimate cause of the collapse of those buildings. A couple different factors. One, just the intense heat caused the metal to weaken, but then at the same time, there were longer spans that were being supported in compression. So the coupling of the greater stress and the reduced strength just ended up leading to a buckling failure that resulted in that eventual collapse. I'm sure that the condo collapse in Miami is going to be another example of that, just an issue of the columns not being able to support the weight above. But in addition to those examples, the same thing also applies to mechanical parts like piston rods, valve springs, hydraulic shafts. Any of those components placed in compression could also have that potential to buckle. And so just like we have our failure theories for static loading, von Mises maximum distortion energy theory, maximum shear stress theory, we also need a failure theory to predict buckling. And that kind of just touches on then that idea of stability and equilibrium. And this kind of touches then on what you have learned or will learn in your ME 352 dynamic systems or controls class, when they start talking about different types of systems. But if you're looking at stability and equilibrium, we have a couple examples of, say, just a ball in a bowl shape, which would be a stable equilibrium. If you apply a force to the ball, a perturbation, and you move the ball away from kind of the ideal point here in the center, when you let that go, it'll return back eventually to that ideal position. So that's a stable equilibrium position. If you're looking at a flat plane, if you move the ball away, it's not going to come back. It's just going to stay where it's at. So that's a neutral equilibrium. It's not going to go any further away from that ideal position once you let go of it. It's just going to stay where you left it. And then you get to unstable equilibrium. If your ideal point is at the top here and you move it to the right, say gravity is going to take over, and once you let go, it's just going to keep going further away from your ideal point. And so that kind of gets then into control theory and really developing stable systems, and also working to control unstable type systems to keep those at their nominal position. And so in the case of column buckling, just depending on the geometry, the boundary conditions, material properties, and that compressive load P, as that increases, a column will eventually reach an unstable equilibrium situation where it's going to have widely excessive lateral deformations in comparison to the loading that's being placed on it. And that's going to cause it to lose the weight carrying capability of the column, causing that structural collapse or that mechanical failure. And so we can look at just a general definition for a column where it's pinned, and we have a given length of the column L. X will be along the axial direction, Y will be in the transverse or lateral direction, and we have a compressive load P placed on here. And if we cause a displacement Y in the center, say we place a force on there, and it causes a displacement, say in the Y direction, we would still have our vertical forces and a reaction of our axial load acting on that. So we'd have the given free body diagram. And even without that force present, just say we have a displacement in the Y direction resulting from that buckling, we would be able to draw a free body diagram of that case. Once we remove that force. And so kind of think about it in that manner of that last page where you cause a perturbation and then you let go of that, what's going to happen. And so this is a free body diagram then of what's going to happen at that point after you have that displacement Y on there. And so when you draw your free body diagram, again, you're just going to have your axial load from your reaction acting upward. You would have the same axial load acting downward. You can verify that just by summing forces in the Y equal to 0. Those are going to be the same. But the other thing that you note is that causes a moment couple. That would create a clockwise moment about this bottom point. And so then you would need an opposing internal moment at that cut to counteract that. So that's going to be a counterclockwise moment. And so if we sum our moments, I guess at this example, I sum moments counter or clockwise. And so this is about 0.1 here. We'd have a P times Y, just force times moment arm minus the M for our internal moment. And solving that then, again, M then is equal to, remember, a minus EI d squared Y dx squared from our bending discussion. And the main thing that needs to happen for it to remain stable is that moment needs to be greater than or equal to PY, which is kind of an overturning moment. And so if we plug that in there to the equation there, we have EI d squared Y dx squared plus PY is equal to 0. And since that is equal to 0, I guess we're just dividing through by EI, both sides. So we have P over EI there then in the second term, and 0 divided by anything, still 0. So we just kind of got it into a cleaner form in that second relationship. And so what you kind of recognize this is a homogeneous second order linear ordinary differential equation where y is only a function of x. And so remembering back to Math 321, homogeneous just means the right-hand side is equal to 0. Second order means that the highest derivative is equal to 2. And linear ordinary differential equation, y is only a function of x. It also has constant coefficients. Out in the front here, we have unity for the first one and p over ei for the second term. And Dr. Tietz was the one that taught me Math 321. Oh, that must have been back in the spring of '96. And he always talked about differential equations as a big bag of tricks. Just based on the type of equation, you just need to open your bag of tricks in order to solve for the particular differential equation. And so for that situation, you have the general solution to solve for this homogeneous equation, just as y is equal to c1 times the sine of x square root of p over ei plus c2 cosine x over times the square root of p over ei, where c1 and c2 are really the constants of integration. And again, we're just using boundary conditions to solve for C1 and C2. And with our definition of X and Y, if this being the origin here at the bottom, at X equal to 0, the displacement in the lateral direction has to be equal to 0 because it's pinned. And so that's a handy one to put up in this location, because y of 0 is equal to c1 times the sine of 0. 0 is out in front here, so everything multiplied by that is still going to be 0, plus c2 times the cosine of 0 is equal to 0. And so sine of 0 is 0, cosine 0 is 1. And so that tells us then that C1 could have any value towards that, and that would still be 0 because it's multiplied by 0. With cosine 0 equal to 1, C2, if that were any finite value, it would not be equal to 0 on the right-hand side. So it just tells you that C2 is equal to 0. And so that drops off an entire term for our general solution for this pin-pin case. And then we know at the other end, at the top, where it's pinned again, at x equal to L, y is equal to 0 there too. And so we can, now we know C2 is equal to 0, we can put y of L in here and solve for C1. And I'm trying to get both of those on there at the same time. So we have y of L is equal to C1 sine of L times the square root of P over EI. Where we're at next. And so this is also equal to 0. I should have put that in there, but this is also equal to 0. And so you have two choices. One, C1 could be equal to 0, but that'd be a trivial solution because then y would always be equal to 0 if both C1 and C2 are equal to 0. And so your second option is that the sine term of L times the square root of P over EI is equal to 0. And that leads then to a non-trivial solution. It only occurs at those specific instances. And so we're looking at this second situation as a non-trivial solution and carrying that forward. And looking at sine, we know that sine is going to be equal to 0 at sine of 0, pi, 2 pi, 3 pi, 4 pi. And so sine of n pi is equal to 0, or n is equal to 1, 2, 3, all the way up. And so we identify then that this term in the parentheses, L times the square root of P over EI has to be equal to N pi. And so with that, we can determine then what a critical buckling load is and solve for P. And we just need to square both sides and move things around, so we end up with the N squared pi squared EI over L squared. And the smallest possible load will occur when N is equal to 1. When we put N equal to 2 in there, that would give a larger P value. And so the critical buckling load is when N is equal to 1, and that'll give us pi squared EI over L squared. And so what this is defined then as is Euler's buckling load that was developed back in the 18th century, 1757, quite a while ago. But it gives you then a relationship to determine what the critical buckling load is, a force. And so that's one unique thing, is that all of our other failure theory that we looked at last week were stress-based failure criteria. So we're looking at the state of stress. This is posed in terms of determining what the critical load is at which buckling will occur. And we see that's a function of the material properties, the Young's modulus of the material, the area moment of inertia for the cross-section that we looked at in chapter 6 with bending, and also the length of the beam. As the beam becomes longer, the potential for buckling increases, and that's at a squared rate. So there's a greater emphasis on that as the length increases. The other thing that you'll notice is there's one thing that's missing out of here, is that you find that it's not a function of the strength at all. And so your cheaper A36 steel is going to have the same potential for buckling as a very expensive high strength steel. And so spending the extra high dollars for the high strength steel doesn't really matter in terms of buckling. It's really a matter of the elastic stability and not the strength. And as you went through MET 231, 232, I think you probably had an opportunity to see that. I always refer to what the metallurgical engineers do as kind of a black magic. It's amazing. You have a steel material, and if you take that through various heat treatment processes, you can change the microstructure and how that forms. And that change in microstructure can have a significant impact on the strength of that material. But one thing it doesn't affect really as you go through that heat treatment process is the Young's modulus. That stays fairly consistent through those heat treatment processes. It's just the strength that is affected. And so in that scenario, you've increased the strength, but the Young's modulus is the same. So it still has the same potential for buckling as if it hadn't gone through that heat treatment. And so that's another reason buckling is really important to consider when you're looking at really loading things greatly in compression. You're picking, say, a high strength steel because you're like, well, it has a higher yield strength, so we'll be good with that from a stress-based standpoint. But then from a buckling standpoint, you're still dealing with those compressive stresses, and the higher strength really isn't playing into your favor at all. So that's why buckling really has to be evaluated critically for those compression members. That really gives you P critical. I guess if you want to, you can then go through and look at that a little bit further. We still have our general form, y is equal to C1 sine x times the square root of P over EI. And so if you put our P critical in for P, pi squared EI over L squared, we have y is equal to C1 sine x square root of pi squared EI over L squared divided by EI. So the EIs will cancel. We have pi squared over L squared square root, so those come out from underneath the square root sign, and we're then left with y is equal to C1 sine pi x over L. And at x equal to L over 2, we know that's going to be the maximum lateral deformation. If we go back up here, at this point in the center is where the maximum lateral deformation will occur. And so when you put that in there in L over 2, the L's will cancel and you'll be left with a pi over 2. So we find that y is equal to C1 sine of pi over 2 is going to be equal to our maximum lateral deflection. Sine of pi over 2, 90 degrees, is just equal to 1. And so it tells you then that C1 is going to be equal to y max. Your maximum deflection. And so you could pose that in terms of y max instead of C1. So y is just equal to y max times the sine of pi times x over L. The interesting thing about that is it really just explains that that shape that it takes in terms of that sine expression, essentially a sine wave then. But y max is kind of ill-defined then at that point. It really depends on how much you perturb that away from the ideal vertical position. And so that's just kind of arbitrary. But once you perturb it a given y max position, you would know the y is a function of x along the entire length of the column. One thing you can do if you want to switch from knowing the critical buckling load, you could solve then what the critical buckling stress is. And so there's a couple ways that you can do that. You can just divide through by the cross-sectional area and that'll give that for you. We'll look at that here in a second. But then we'll also pose that in terms of some other quantities as well. First, we'll define the radius of gyration, and that's just the square root of the area moment of inertia divided by the cross-sectional area. And remember, this is length to the fourth divided by length squared. So that'll be a length squared term coming out of this. And then square root of that will give you a value of length. And so radius of gyration has units of length associated with it. And you can rearrange that. A is just equal to I over the radius of gyration squared. And so we'll use that as we move forward. But your critical stress then for elastic stability based on Euler's method is just your P critical over that cross-sectional area. And so you could calculate your cross-sectional area normally if it's a circular shaft, just pi d squared over 4. You can have your critical Euler's buckling load based on that. Or we can substitute this in I over the radius gyration squared and bring in our relationship for P critical and get this into a what's defined as a slenderness ratio. And so P critical, remember, is pi squared EI over L squared. And A is I over RG, so that radius gyration squared. And so with that, the I's will cancel. And we're left with a pi squared E over radius of gyration squared over L squared. And to simplify that, instead of placing the radius of gyration up above, we just divide that through on the bottom from L. So L over RG quantity squared. And this is defined then as the slenderness ratio, looking at the ratio of the length to the radius of gyration. Pretty sure that's, I think we'll see that in the notes coming up. What we derived that for was really for pinned condition, but we could have other end conditions that that sometimes are more susceptible to buckling or less acceptable to buckling. And so to account for that, our slenderness ratio, we can redefine that as an effective length for the beam based on the pin-pin condition. And so then if we start looking at other boundary type conditions, or say one end is pinned and one end is fixed, we can define a theoretical effective length as if it were a pin-pin condition. And so for pin fixed, the fixed end is going to have a zero slope at that point, so it's not allowed to rotate as our pinned condition was. And so it's not going to be as prone to buckling in that scenario. So the effective length is only 70% of the actual length. And so 0.7 times L will give you the effective length for a pinned fixed condition. Fixed is even better, with both ends not being able to rotate. The effective length is half the actual length. And for a fixed free condition, that's worse, because not only can it be allowed to rotate, one end is free to deflect laterally as well. And so that effective length is twice the actual length. And so this is more of a worst case scenario that you might be looking at there. In addition to kind of these theoretical values, one thing that you'll start looking at, since a lot of these compressive members show up in buildings and things like that, it shows up a lot in civil engineering. And so in addition to kind of the theoretical limits, this might be what you want to use if you are going through and placing safety factors on there that are desired for the particular application. But then you also have, if you're looking at design codes and meeting the design codes, there's the American Institute of Steel Construction that sets limits on defining that effective length. And so you can see they are increasing those from the theoretical limit. So you kind of have a built-in factor of safety. They really don't want you to use the 70% of the length. They want you to consider a beam that's 80% of the actual length. And all these are just slightly bumped up a little bit to have a built-in factor of safety based on that limit. In addition to these that are defined here, you might have additional factors of safety that are required in addition to this limit on P critical. So if we look at an example, say we have a 24-foot long A36 steel tube used in a pin-pin configuration, the one that we just looked at. The outer diameter is 6 inches, the inner diameter is 5.5 inches. What we want to do is find the maximum compressive load. And so E from the textbook is 29 times 10 to the 6 psi. The area moment of inertia is pi over 64 times the diameter outer to the fourth minus diameter inner to the fourth. That's 18.7 inches to the fourth. And then the length is 24 feet long, 12 inches in a foot. We'll give you 288 inches. And so P critical then is pi squared EI over L squared. And just placing those in there, we find that the units that would have came out is 64,500 pounds. And then I converted that to 64.5 kip. And so what about just compressive type stress? A36 steel, the 36 represents the yield strength. And so remember sigma is equal to P over A. And if we define the yield as the limit of what we'd want to go to, our P value would be the yield strength times the area. So 36 KSI times 6 squared minus 5.5 squared divided by 4 times pi, which is our area, will give us 162.6 kip. And so we see that for this example, the critical buckling load would dominate. It'll buckle before it ever yields due to a compressive loading, 64.5 kip. And the yield loading that would be needed is about 2.5 times what would be needed to cause that to buckle. So it's not just a little bit more, it's quite a bit more to reach that point. And so we have a few lecture notes here. We have a couple more pages. And what we were looking at really was just Euler's buckling load, which really works well for long, slender columns. Once you start getting shorter columns, short, stubby columns, then they're less likely to buckle. And so we need different criteria to account for that. And so when we look at kind of what we've derived already for a critical stress based on Euler's method, pi squared E divided by the slenderness ratio squared. And yeah, I was right, that ratio there is known as the slenderness ratio. For Euler's formula to hold and to be valid, the sigma critical value here has to be less than the allowable stress. And the allowable stress is defined by the American Institute of Steel Construction as half the yield strength. And so once the sigma critical goes greater than half the yield strength, then you start getting into more of a short, stubby beam less likely to fail by buckling, and the yield strength becomes a concern. And so if we take that ASCII criteria into account and plug that in, we have pi squared times E over the slenderness ratio squared is equal to 0.5 times the yield strength. We can rearrange that to solve for the slenderness ratio, moving that to the other side, this down, taking the square root of each side. What we would end up with is square root of 2 times E pi squared over the yield strength. And so if the slenderness ratio is less than this value, square root of 2E pi squared over the yield strength, then Euler's formula does not work. And this is really known as then the tangent slenderness ratio. And for those cases where Euler's formula does not work, there's Johnson's buckling criteria. For what we're going to do in ME 316, we're going to focus solely on Euler's formula for long, slender beams. And I'm just kind of giving you some insight into looking at the Johnson criteria and kind of a preview to what you'll be looking at in machine design. And so I didn't want to talk about Euler's formula without discussing Johnson's formula, so that you know that there's a difference between a long slender beam and a short stubby beam. And so that you're kind of prepared for that as you go into machine design. But Johnson's formula then, sigma critical Johnson, is just that P critical defined by Johnson divided by the cross-sectional area. And he has it set up in terms of the yield strength. So the yield strength minus the yield strength squared divided by 4 pi squared E times our slenderness ratio squared will give us the critical stress based on Johnson's formula that would result in buckling for those short stubby beams. And again, sigma critical is the same as pi squared E over LD RG squared. Let's see. What we're doing now is where does Euler and Johnson meet? And so it would meet at that tangent point where the critical stress would be pi squared E over the slenderness ratio squared at that tangent point. And that's equal then to the Johnson equation as well. And so this is Euler's equation on the left and Johnson's criteria on the right is what we're seeing. And then what we're going to be doing is just taking a look at that. And so if we were to plot that, then we would plot that as the compressive stress that we're dealing with versus the slenderness ratio, the effective length divided by the radius of gyration. And again, we're dealing with compressive stresses, and so this is really just the magnitude of stress, remembering that it's a negative stress that we're dealing with. If we were to plot Euler's formula based on the above, it would just be kind of an exponential type of curve that would just start going straight up. Then you would have your yield strength of the material. I didn't write that in as the yield strength, but that's what this flat line represents, so that everything above that would be a yielding area. And then when we look at Johnson's criteria, that's just a second order relationship. So that's going to be a parabolic curve. And that essentially opens downward with the negative sign in front of the squared term. So that opens downward and it just reaches a common point at that tangent slenderness ratio. So this would represent then the LE over RG tangent point. And so essentially to the left of that, you would use the Johnson criteria. To the right of that point, you would use the Euler criteria. If your state of stress is beneath that two curves, the Euler and the Johnson, it would be safe from buckling. If you go beyond that curve, out in this area, it would fail due to the Euler formula and the long column buckling relationships. If you're in this area, it would be failing by exceeding the Johnson criteria for short stubby beams. And this then kind of represents the critical stress. And so just the same thing that we saw on the distribution of real materials failing for the failure envelopes, we saw that they weren't all falling right on the line. They were distributed about that line. And what we'll see with buckling is that is it has a wider range of scatter. And so where this might be the ideal line based on the theory, for a real application, you could see failures occurring beyond that a little bit. You could see them occurring well below that too. It's really dependent upon the geometry of the cross section and is really susceptible to any imperfections in the material and the geometry, things like that. And so that could lower that buckling load quite a bit just based on material imperfections during the manufacturing process. And so when you start looking at ASCII's criteria, they will then establish design curves well below this theoretical limit so that you're well below that potential for buckling. And so that's what you'll see with the ASCII criteria is just design curves placed below that. Well, let's see, I have some examples that are discussed. I'd have to look to see if that's referencing our current textbook. But there was just kind of a separate discussion just showing how the geometry has a significant impact on the critical buckling load. Another thing that we looked at in torsion, when we move the material further away from the center to make a tube, we saw that the polar moment of inertia would increase. And so it could theoretically take a larger shear stress in that scenario. But then you have the potential for localized buckling. And so with circular tubes or things like that, they also have that potential for localized buckling. You have your overall buckling that could occur that we looked at for pin fix, that type of thing. But you could have localized buckling where things just kind of collapse into like an accordion through that buckling process. And so there are also concerns for localized buckling when you're dealing with thin-walled members. And I think one of the best things for evaluating localized buckling is that ROARC's formulas for stress and strain that I brought up before. There are some other ones, advanced mechanics and materials. And then they had a more recent version as well. And I think the rest of this is just, again, solving that tangent ratio that we had before. I think we already stated that previously. LE over RG is 2E pi squared over the yield strength. And so we're seeing that again through that same derivation, setting up the left-hand side and the right-hand side. Just showing that that is indeed the tangent slenderness ratio. So I don't think we really need to go through that derivation again. I'll just leave that for you to look through. But the main thing coming out of that again is that when your slenderness ratio is less than that tangent ratio, use the Johnson criteria. When your slenderness ratio is greater than that tangent point, use the Euler equation. And again, what we'll be focused on is just looking at long, slender columns. I don't believe your Hibbeler textbook even mentions Johnson's criteria. So all the problems in there are for long, slender columns. I just wanted to give you that preview that that doesn't work for all columns, that there's another relationship that's used for short, stubby columns. And so I think that's it. I guess, Jordan, do you have any questions about that?
No, not at the moment.
Yep, and so the problems that we'll find in Hibbeler's textbook is just basic looking at the critical buckling load, or what that critical buckling stress is for a long, slender column. And those relationships, you just really kind of have to remember that P critical relationship and solving out what the effective length is just based on the boundary conditions. So it becomes pretty straightforward in solving those particular problems. And then as you get into machine design, you will look more at that both of those criteria, the Euler criteria or the Johnson. You'll have to decide based on the tangent slenderness ratio where you're at and which criteria would apply for that location, and then solve that then accordingly. The other issue that you'll run into with machine design, looking at that in that course, is the vertical loading that was placed on the column was concentrically placed, so it wasn't offset. You could have another column type situation where the load is offset from the axial direction. So even before you have a perturbation, you already have an internal moment within your beam. And that's really referred to as an eccentricity, where you'd have to redraw the free body diagram and then look at it from that standpoint. But what that really does is it changes your non-homogeneous, your homogeneous equation where you had your right hand equal to 0. It changes that to a non-homogeneous where you have a term on that right-hand side. And that's just a different bag of tricks to solve for that particular differential equation. But that's another class of buckling type problems when that load isn't placed concentrically on there. And so that gives you a little preview of other failure mechanisms that you're going to be looking at in machine design. The other two types of failure mechanisms that we aren't going to discuss here in solid mechanics are one, fracture mechanics, when looking at brittle materials, they generally do not fail by yielding. They fail by the cracks opening and propagating and breaking in that manner. And so there's the field of fracture mechanics that looks at the critical stresses that would cause a material to fail by fracture. And then there's fatigue failure mechanisms that you'll look at. And so everything that we've done so far is looked at static loading conditions. Well, what if you take an object and you repeatedly cycle that back and forth between, say, a tensile and compressive loading condition? Think of bending a paper clip back and forth. Eventually it's going to break. And so the same thing would happen with, say, a rotating shaft. As it's rotating through, it's cycling between tension and compression, and can lead to fatigue loading. And so in Machine Design 1, ME322, you start looking at that as well, looking at how many cycles would that shaft have before failure. For steel shafts, you can design those for infinite life as long as you keep the stress low enough. Non-ferrous materials like aluminum, they don't have an infinite fatigue life. That always decays with time, cycling it back and forth. And so they do have a finite life associated with them. But you'll get a look at buckling, fracture mechanics, and fatigue as you go into machine design. And then you'll get a touch on some of the machine element components as well in that course. And that's what I cover in Machine Design 2, more thorough in depth on energy methods, and then looking at machine components, fasteners, springs. Gears is covered in Machine Design 1, so I don't repeat that in Machine Design 2, but looking at weld analysis and all those things. But I think we'll call that good for today. Friday's lecture is going to be looking more than at kind of an overview of energy methods and using that as a means to solve for displacements and rotations for more complex problems. You can do that in an organized fashion and be able to solve displacements for more complicated situations than what we've looked at already. So we'll call that good for today, and then we'll see you on Friday.
Yep, see you on Friday. Or well, probably not.
Yep. Have a safe trip, Jordan.
I will. Thank you.
Yep.
Bye.
Yep. Bye.